Welcome to Signal Ahead. I'm Alfred. Today's briefing, Theory and Foundations, Physics plus Math. Friday, July 3. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. Let me tell you something that at first glance looks like nothing more than a scheduling coincidence. In a single stretch of days this summer, a complexity theorist announced a lovely piece of news about bipartite matching, a problem about pairing things up, being placed in a class called NC, meaning it can be solved efficiently in parallel, many hands making genuinely light work. In that very same window, a group of physicists were reformulating cosmological correlators, the statistical fingerprints of the early universe. By observing that deep inside the cosmic horizon, every mode of a field simply oscillates like a plane wave in flat, featureless space. And elsewhere, someone was proving that certain Feynman integrals, those fearsome objects that encode particle interactions, are not merely complicated functions, but are in fact completely monotonic. Every derivative has a fixed sign and even Steele-as functions, which lets you approximate them with rigorous, provable bounds. Now, on the surface, these have nothing to do with one another. One is theoretical computer science, one is cosmology, one is quantum field theory. But listen to what they share, because this is the thread I want to pull on across our conversation today. In each case, the advance comes not from computing something harder, but from recognizing that a monstrously complicated object secretly has a simpler structure hiding inside it. The matching problem was thought to resist parallelization. It turns out it doesn't. The cosmological correlator looks like it demands you wrestle with the full curvature of spacetime. It turns out you can decompose it into flat space pieces you already know how to handle. The Feynman integral looks like an arbitrary tangle. It turns out it belongs to a class of functions so well-behaved that positivity alone constrains its shape. State of the field right now is defined by a kind of relentless search for hidden simplicity, for the flat space plane wave lurking inside the curved one, for the monotone function lurking inside the integral. And that, I'd argue, is the through line connecting foundations of physics to foundations of mathematics at this particular moment. The frontier is no longer only about pushing into greater complexity. It's about a maturity of technique in which we learn to see the skeleton beneath the flesh. Consider the physicists rebuilding the standard model gauge group out of the exceptional Jordan algebra and octonions, those eccentric non-associative cousins of the real numbers. The whole gambit there is that the seemingly arbitrary particle content of our universe, the specific groups that govern its forces, might be forced upon us by an algebraic structure that leaves almost no room for choice. Simplicity again, but of a demanding kind. Not this is easy, but this could hardly be otherwise. Or take the quieter, more sociological signal. When the head of state issues an executive order about quantum computing and journalists come running to the theorists for comment, you're watching a foundational field being pulled into the machinery of national policy and funding. That's a marker of where we stand too. The abstractions have consequences. Bipartite matching in parallel isn't only a beautiful result. It's the kind of thing that, decades downstream, reshapes how we schedule, allocate, and route the physical world. The distance between the blackboard and the budget line has never been shorter, and that creates its own pressures on what gets funded, what gets hyped, and what gets quietly ignored because it doesn't fit the narrative of imminent revolution. There's also a deeper current worth naming at the outset. Across these papers, you find a recurring obsession with what happens at boundaries and horizons, the edge of a black hole, the interface between two topological insulators, the light cone separating time-like from space-like, the moment a mode crosses the cosmic horizon. Physics keeps discovering that the interesting information lives on the surface, on the boundary, on the edge, and that the bulk can often be reconstructed from it. Mathematicians, meanwhile, are refining the algebraic languages bialgebroids, cosical twists, chiral quantizations, precise enough to describe exactly how a deformed quantum structure sits atop a classical one. Both communities are converging from opposite directions on the same suspicion, that reality is layered, and that the deep description lives at the interface between the layers. So here is the argument I want to build with you over the next while. First, that the current state of theory is best understood not as a race toward complexity, but as a disciplined hunt for the hidden simple structure, the flat inside the curved, the monotone inside the tangled, the forced inside the arbitrary. Second, that physics and mathematics are quietly using the same moves, boundary reconstruction and structural rigidity, even when they don't cite one another. And third, that this is happening precisely as these fields collide with policy and money, which sharpens both their promise and their peril. Let us begin, then, where the simplicity is hardest won, with the question of what it even means for a hard problem to secretly be easy. There is a temptation, when you survey a week's worth of work in the foundations of physics and mathematics, to see only a scatter of unrelated preoccupations. Here someone is worrying about black strings and their decoupling limits. There someone else is proving that bipartite matching can be done in parallel. A third is coaxing numerical data out of the inverse Galois problem, and a fourth is reaching for octonians to explain why the standard model has the gauge group it does. It looks like noise. It is not noise. Beneath it runs a single deep current, and once you learn to feel it, you cannot stop feeling it. The current is this: the field is quietly relocating its trust from the answer to the structure that guarantees the answer. That is a subtle shift, and it deserves unpacking. For most of the 20th century, the goal of a calculation was the number at the end, the cross-section, the eigenvalue, the probability. You did whatever it took to get there, and the getting there was often an ugly business of expansions patched together, region by region, each valid in its own little kingdom, none of them speaking to the others. What I see now, again and again, is a refusal of that patchwork. People want a single representation that is valid everywhere, that carries its own guarantee of correctness inside it. Consider the way certain cosmological correlators are now being computed. The old approach fought the curvature of spacetime head-on, integral by painful integral. The new move is almost impudent in its simplicity. It observes that deep inside the horizon, every mode is just a flat space plane wave, and only near the horizon does the geometry announce itself. So you perform a transform that dissolves the curved space object into a continuous chorus of flat space plane waves, each dressed by a kernel that quietly stores all the geometry and dynamics. The hard time integral collapses into an elementary one, and crucially, the result comes out as a single, rapidly converging series valid across the whole kinematic domain, no patching, no seams. The structure of the representation is what does the work. The number falls out as a byproduct of having found the right frame. You see the same instinct in a very different corner, where Feynman integrals are being tamed not by brute evaluation, but by exploiting a property they turn out to possess, complete monotonicity, and in favorable cases the stronger Steelt's property, meaning every derivative has a fixed sign. Once you know an object belongs to such a class, you can bootstrap it from its differential equation with no boundary data at all, and this is the part that matters with rigorous, provable bounds. The positivity is the guarantee. You are no longer trusting a number you computed. You are trusting a structural fact about the kind of function it must be. And here is the beautiful thing. This is exactly what the pure mathematicians have been doing all along, and the two traditions are converging. When one proves that bipartite matching sits inside the complexity class NC, that it can be solved in parallel in polylogarithmic depth, one is not finding a faster algorithm in the engineering sense. One is establishing a structural truth about where a problem lives, what resources it fundamentally requires. That is a statement about the architecture of the possible, not about any particular run of a machine. The same spirit animates the effort to build a bulk edge correspondence for topological insulators on curved interfaces, where a physical fact about edge currents is pinned to a product of a bulk topological index and a purely geometric intersection number. The physics is guaranteed by the topology. The invariant cannot lie. Notice what all of these share. In each case, the trustworthy thing is not the endpoint, but the invariant, the class, the representation, the positivity, the piece of structure that could not be otherwise. When someone asks whether octonians and the exceptional Jordan algebra can produce the standard model gauge group, they are asking the deepest version of this question. Is the messy particular content of our universe secretly the shadow of a structure that had no choice? When someone builds a deformation obstruction theory for chiral quantizations and finds it controlled by de Rham cohomology, they are saying that the freedom to deform a physical theory is not arbitrary. It is bookkept by a cohomology that already existed, waiting. The abstraction is the guarantee. This is why the week's work is not scatter. The physicist reaching for a Laplace kernel, and the topologist counting intersection numbers, and the complexity theorist locating matching inside NC are all, whether they would phrase it this way or not, making the same wager. The wager is that the reliable knowledge, the knowledge that survives, that composes, that you can build the next thing on top of, is structural knowledge. It is the knowledge of what a thing must be, given the frame it lives in. Answers are perishable. Structures are load-bearing. And the deep current beneath all this noise is the slow, collective decision to build only on what will bear the load. Welcome back, and let me try to pull the threads together, because if you've stayed with me through the technical thickets, you'll want to know what the shape of it all means, not just the individual results, but the pattern they trace. Consider what we've been circling. A proof that bipartite matching sits inside the complexity class NC, meaning it can be parallelized efficiently. A claim that the gauge group of the standard model, the whole scaffolding of particle physics, falls out of the exceptional Jordan algebra, that curious structure built from octonions. A method for computing cosmological correlators by noticing that deep inside the Hubble radius, every mode simply oscillates like a plain old flat space plane wave. A second-order diagnostic for dark energy that lets you read the curvature of the density trajectory rather than merely its slope. What do these have in common? On the surface, nothing, and that surface disagreement is precisely the point I want to draw out. The first implication worth watching is the quiet triumph of the right change of variables. Notice how often the deepest progress comes not from brute force, but from finding the coordinate system in which a hard problem becomes an easy one. The Laplace space approach to cosmological correlators does exactly this. It takes a fearsome curved spacetime time integral, dresses each mode in a kernel, and collapses the whole thing onto elementary flat space integrals. The geometry hasn't gone away, it's been absorbed into the kernel. Similarly, when someone recasts the violations of Schwinger-Dyson identities as projections of a single score mismatch field, they've found the variable in which a whole hierarchy of relations becomes one geometric statement about distance from equilibrium. Watch for this move everywhere. When a field suddenly accelerates, ask whether someone changed variables and made the impossible integral vanish. That is not a trick. It is often the discovery itself, wearing modest clothes. The second thing to watch is the recurrence of universality, the maddening, beautiful fact that different starting points converge on the same answer. Distinct parent geometries of near-extremal black holes yield the same logarithmic temperature dependence at one loop, and the interesting question is not that they agree, but why the relevant spectral data become blind to the details you thought mattered. This is a signal in the cryptographic sense. When many roads lead to one destination, there is usually a structure enforcing the convergence that we haven't yet named. The Ising model on a random surface flowing to a specific minimal model, the proposal that high-energy scattering behaves the same regardless of charge, an extension of the equivalence principle beyond gravity itself, these are all instances of nature refusing to care about our bookkeeping. And where nature refuses to care, there is a conservation law or a symmetry hiding, waiting to be made explicit. The universality is the smoke. The fire is the principle you haven't yet written down. The third implication is more sociological, and I'll be candid about it. Notice how much of this work is now collaborative in a new sense, challenges to generate numerical data for the inverse Galois problem, databases of modular forms, the marriage of human insight with machine-assisted computation. The frontier is not moving only through solitary genius scribbling at a mountain science camp, though there is charm in that image. It is moving through infrastructure-shared datasets, competitions, the patient accumulation of examples that let a pattern become visible before anyone can prove it. Watch the databases. The next great structural theorem in number theory may announce itself first as an anomaly in a table. And what should you, watching from outside the equations, actually take from this? I'd say three things. First, distrust any story that treats these domains as sealed rooms. The same operatic deformation theory that quantizes a Poisson algebra reappears in chiral form, controlling deformations of vertex algebras. The tools migrate. Second, the second-order view keeps proving richer than the first. The continuity equation tells you where the density is going, Differentiate once more, and you see how the equation of state itself is evolving. The lesson generalizes. The instantaneous value hides the dynamics, and the dynamics live in the curvature. When someone offers you a first-order summary of anything, an economy, a technology, a threat, ask what the second derivative is doing. That is where the surprises breed. Third, and finally, hold on to the distinction between what is encoded and what is explicit. The information about dark energy's evolution was always present in the full solution. It simply wasn't visible in the equation you happen to be looking at. Much of theoretical physics is not discovering new facts, but re-representing old ones until they confess. The signal was always in the data. Somebody just had to Laplace transform it, or change basis, or count the shortest paths on a graph until the black hole's curvature revealed itself in the statistics. That, more than any single result, is the thing to watch, not the answers, but the coordinate systems in which the answers finally become obvious. Until next time. That's the signal for today. The noise will keep coming, we'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.